Okay, then we're going to go on to Taylor's theorem, section 2.5. This is probably the piece of calculus that I use more than any other piece of calculus in my research. I'm doing numerical approximations for differential equations. It all comes down to just Taylor expanding everything in sight. So this I'm going to say is important. Okay, so the idea is we have a function. Let me get your test. I can't remember your last name. Okay, I knew that. There you are. Okay, so we have a function. We want to try to come up with some kind of approximation of it that works at least locally. Okay, so I'm going to say I have some function that does whatever. I'd like to approximate it well at this point. This point I'm going to call x0. So we zoom in close to x0, maybe in this region, and we say, if we take this and blow it up, we take this box and blow it up, what's the function doing? The function is doing something like this. It looks pretty close to a straight line if we zoom in on a small enough piece of it. So here, you might say, zooming in, it looks close to linear. Right, it's well approximated by a straight line. So maybe if we're just interested in the behavior of f close to x0, maybe we can find a straight line that would give us a pretty good result and would be a lot easier to work with than a complicated function. We might want to improve this a little bit. So if we want to improve this, what's the next best thing from a straight line? A parabola, yeah, a quadratic function. So if we want to improve this estimate, so let's try a quadratic approximation. Okay, so if I draw my function again, something like this. And now I say, I'm starting here, so again, I'm interested in what happens at x0. I'm going to try to draw a parabola that matches that. George, I'm going to grab your test. There you go. I want to have a parabola that matches this. I want to keep it close as possible here. So I want to match the value here. I want to match the slope here so that it follows as well as possible. And then I'll try my best I can to match the curvature here. And I might get something like this. And this is doing probably better than the straight line function, right? This is, I haven't proved anything, but it looks like it's doing better. It looks like it can follow the curve more because we've introduced the ability now for our approximation to have some curvature to it. And a cubic might do even better. So if we try to do a cubic, so here's my function. A cubic approximation might do something like this. And again, it might track this even better. That's what we're hoping. By introducing more degrees of freedom into our approximation, right, more terms into our approximation, we can do a better job. But again, each term is just a polynomial term, which is easy to work with. It just means we have to know how to add and we have to know how to multiply, which is great if you're using a calculator or something, and those are the things your calculator knows how to do. It knows how to add, it knows how to multiply, and wants to use those abilities to compute sine functions or exponential functions without having lots of complicated work to do. OK, so we're looking near x0. And we're looking at what f does near x0. So what are the conditions we should put on our polynomial approximation? What's some reasonable things that we might ask it to do? Yeah. Okay, we want it to be bounded, sure. Polynomial approximation is going to be locally bounded, certainly, and probably not globally bounded. What are some other things, right? We're trying to approximate at the function f. So let me add this, trying to approximate f. So what we really want is that somehow f of x is approximately equal to some polynomial. Maybe an nth degree polynomial. And we need some conditions, some constraints that let us decide what these coefficients, what these a's are. Yeah? It should be differentiable at x0. And what should its value of its derivative be there? Okay, a1 is the value of the derivative. How should that relate to the function we're trying to approximate? It should be the same, right? So this is reasonable. We want to approximate things well near x0. So it's reasonable to say, let's make f at x0 equal to the value of my polynomial here. Let's try to make the derivatives the same so that the straight line starts off going in the right direction at least. If we have more freedom, let's try to make the curvature the same, the second derivative the same. So let's require f of x0 to equal the polynomial at x0. And let's try to acquire the derivatives also agree. The first few derivatives, however many we can get. Okay, so I'm going to give this polynomial a name. Tn of x equals a0 plus a1 x minus x0. It's an nth degree polynomial. So this is our approximation. And now we're going to try to solve for the a's, and we should be able to hopefully do this. Okay, so we start with the function value and say, at the least, if we're going to do a good job approximating near this point, the function and the polynomial should agree with each other. So let's ask that Tn of x0 equals f of x0. Okay, so what happens? I plug in x0 here. Well, this term is 0, this term is 0, this term is 0. Right? There's a reason I've written the polynomial in this way, where I've really centered it about x0, because it's going to make these coefficients easy to solve for. All that's left is a0. So we get a0 equals f of x0. Yes?
What is the term that's before the arrow?
This is f of x0. Okay, so we got the functions to match at this point. We figured out what a0 should be. Now we've got more coefficients around that we want to solve for. So we can keep going and try to make the derivatives match, make the slope match so that our line starts off going in the right direction. So we need the derivative of this function, Tn prime of x. This is going to be, the a0 goes away. We get an a1. We get a 2a2 x minus x0. All the way down the line, and we get an n x minus x0 to the n minus 1. Okay, and then again, we ask that these things agree with each other. So I'm going to plug in x0, the point that I really care about, and say I want my polynomial to have the right derivative at that point. and we're going to see the same kind of thing, right? Plug in x naught, and most of these terms vanish, and all that's left is my a1. Okay, I'll do one more, see if we can find the pattern here. So if n is bigger than 1, I've still got more coefficients around that I can try to match. So let's take another derivative, Tn double prime. This is going to be equal to 2. Bring down a 1 here. So 2 times 1, a2, plus all the way down the list. N, we bring down the n minus 1, an x minus x naught to the n minus 2. Okay, again, I plug in x naught. Most of these terms go away, and I get Tn double prime x naught is equal to 2 times 1 a2. Right? Every time we take a derivative, and it's clear to see in this term here, we're going to bring down another power. It's important to recognize the pattern. And that tells us that, well, a2, sorry, we want this equal to f double prime. That tells us that a2 should be 1 over 2 times 1 times f double prime. And we keep going. So what's the pattern? If I take the kth derivative, what will that look like? So if I'm just taking the k factorial, I'm just taking the kth derivative, right? So you're telling me what you expect because you've seen Taylor series before. But let's actually look at this function. What is the kth derivative of this function? Yeah. It's a k factorial, right? So every time we're moving to the next term, the kth term, so far we've taken, okay, at this point we've taken 2 derivatives, so we brought down a 2 times 1. At the kth term, we've brought down a k minus 1, k minus 2. We've taken enough derivatives that we've brought down k of these terms until there's nothing left up front to become 0. And then we still have our ak here. And we want this equal to the kth derivative of f. Okay, and again, okay, now we get the term that you're itching for me to write down, 1 over k factorial, kth derivative of f at x naught. Okay, and this is saying that if we do this approximation, we approximate at x naught, then the function, the polynomial agrees with the function value here. The derivative is correct here. The second derivative is correct here. The first n derivatives are correct here, which means it's trying as hard as possible near this point, to follow this curve. Now, things can go way off track, way out here, but what we're talking about is what's happening close by. Close by, we're trying really, really hard to follow this curve carefully. So that gives us a reasonable way to try to define our Taylor approximation. So let's define the nth Taylor polynomial as exactly what we get when we plug in these coefficients. So Tn of x. Now we're going to start from a 0th order term, that's our constant, and go up to our nth order term. We have our ak. Now we figured out what our ak is. Our ak in general looks like this. Where by convention, right, 0 factorial is equal to 1. And the 0th derivative is just the function itself. So we have our 1 over k factorial fk of x naught times, and then the polynomial term that gets attached to that coefficient. Okay, so this part you've definitely seen before. You've seen this polynomial. Now, the thing that you should be worried about is, great, we wrote down a polynomial. At this one particular point, the function and the derivatives all match. But why does that tell me anything useful as soon as I leave that point? Right? How good is this in general? So this is the question we want to ask. Is this actually any good as an approximation? Right? It's no good to say this works well at x naught, because we've plugged in, we already know the values of f at x naught in order to do this. We've had to plug them in here. But is this any good as an approximation of f for x not equal to x naught? Okay, so let me write down the theorem, and then we'll try to figure out why this theorem actually holds true. So Taylor's theorem, which again, this you should have seen before. So we have some conditions where this is going to work well or where this is not going to work well. First of all, obviously, we used the derivatives of f to build this polynomial, so these derivatives better actually exist, right? I can't just put a crazy function that's not differentiable here and expect to be able to do this. Okay, so we're going to suppose that f prime all the way up to the nth derivative, and then I'm going to go one more all the way up to the n plus first derivative. You can weaken that a little bit, but this is going to make the proof easier. Okay, these are all nice functions. So these are all continuous on some interval AB. Right, because we know that a derivative could exist, but that doesn't mean it's continuous. We saw that in the midterm this week. So I'm assuming these derivatives all exist and they behave themselves. Okay, then for any x naught in this interval, so for any x naught in this interval, and for every x in this interval, okay, so I pick my x naught to be wherever I want. Let me grab your test. I pick x to be the point where I want to approximate it, which can again be wherever I want. And now we want to come up with some estimate on the error. Okay, so this is going to say there exists some point, C, between x and x naught, such that f of x is equal to the Taylor polynomial plus a remainder term, and we can write down what this remainder term looks like. The remainder term is going to look a lot like our next term in the Taylor approximation. So the 1 over n plus 1 factorial, the n plus first derivative of f, that's why I need it to be there and be behaving itself. The only difference is, instead of evaluating this at x naught, I'm going to evaluate this at c, and I don't know exactly where this c is. And then times x minus x naught to the n plus 1. Right, this term is our remainder. Okay, so this tells us something about how close this Tn, this polynomial, is to the function we want. It doesn't tell us exactly what the error is, which should make sense, because if we knew exactly what the error was, right, if I had an exact form of the error, then I would just add it back here and I'd get f of x exactly. If I had an easy way to get f of x exactly, I would not be trying to come up with simple polynomial approximations. So we don't know exactly what the error is, but we can say, as long as we know that this guy is a well-behaved, fn plus 1 is continuous. If fn plus 1 is continuous on this interval, it's bounded, right? We know that. Continuous function on a closed finite interval is always bounded, right? So we can put some bounds at least on how big this is. And we can expect that if x is close to x naught, if this is small, so if this is a constant, n is fixed, this is a number. This, we don't know how big it is, but we know it's bounded by some number. Then as x gets close to x naught, this is a small term, and we should get a small error. All right, so we can write that down explicitly. So we notice that. Okay, the limit as x goes to x naught, so as we get close to x naught, that's where we expect this to work well, of our error term. Okay, I don't know exactly what this value is, but I can put bounds on it. We're doing our sandwich theorem or squeeze theorem, whatever you like to call it here. So this is going to be less than the limit as x goes to x naught of 1 over n plus 1 factorial, which is just a number, times the maximum over all c belonging to AB of fn plus 1 of c times x minus x naught to the n plus 1. You have a question?
Max? Would we say inf or max?
Would we say inf?
Supremum or max?
Would we say supremum or max? So remember, it's always a good question to worry about. This guy, I've stated here, this guy is continuous, right? On this interval a to b, which is closed and finite. So whenever we have something that's continuous on a closed finite interval, we know that we have a max that exists. So it's always a great question to worry about. Here, we know we have a max. We know this thing is not going to blow up to infinity on us. And that's why I really needed this extra condition here, that this n plus first derivative behaves itself. Not just that it exists, but it exists and is continuous. Okay, so this doesn't depend on x naught. This doesn't depend on x naught. And we know, again, we have a max. It's finite. This is the only part that depends on x naught, and that is going to go to 0. Okay, so if the limit as x goes to x naught of this thing is equal to 0, then we know that if x is close enough to x naught, this remainder can be made as small as we like, right? In other words, this error term is going to be small as long as we're sufficiently close to x naught. Okay, so this is small. As small as you like, as long as we are sufficiently close to x naught. Yeah.
If we wanted to extend this definition from AB to be the real line?
To be the real line. Yeah, so if you wanted to extend this to be the real line, in fact, it will be enough to say we've picked our x and we've picked our x naught to be somewhere on the real line. The c is actually going to live between these two guys. So I could let this be my closed interval.
Okay.
So yeah, you can do this. And if you happen to know that this is bounded over R, then you could get a uniform kind of bound on that. If not, at least you can bound it by what happens in here. Okay, this is the theorem, which we'd like to prove. I don't know that it's at all obvious that this is exactly the form the error has to take. Again, all we've done is say, let's look at the function, its values at one particular point, and we're somehow claiming this is going to give us a good approximation at other points. So we need to do a little work on that. Okay, so here is the proof of Taylor's theorem. Okay, first of all, if x equals x naught, do you believe this theorem works? Yeah. Okay, I'm willing to call it trivial. I don't like to use the word trivially or obviously because it's a dangerous word. It usually means I can't figure out how to prove this and I'm going to try to bluff my way through. But here I think it's fair to call it trivially. If I plug in x naught here, we've designed this polynomial to equal f at x naught, and this term is clearly going to be 0 there. Okay? So if x equals x naught, this certainly holds. It's not very interesting, but it holds. So let's focus on the case where x is not equal to x naught. The reason I'm making this distinction is because I'm expecting things like x minus x naught might pop up in denominators or something when we do the rest of this proof. So I want to throw this case away. So let's suppose now that x is not x naught. So I'm going to come back to this approximation. I'm going to say, let's write f of x is Tn of x plus some remainder. That's certainly true, right? I can define this remainder as the difference between these two things. And I'm going to go one step farther, and I'm going to say I'm going to ask it to have this form, but I don't know what's out in front here. So what am I going to do? I'm going to fix x. Then I claim there exists a unique number m such that f of x equals Tn of x plus m times x minus x naught to the n plus 1. Okay? And again, I'm not doing any magic here. All I'm doing is saying f of x is equal to t plus some error. I'm choosing to write the error in this form where this is free. Here, this is going to clearly work for m equal to f minus t divided by x minus x naught to the n plus 1. Right? So I'm not saying that this is the same m that will work for every value of x. I'm saying I've fixed my x, I've fixed my x naught. So these are not really functions, they're just numbers here. And when I combine all those numbers and I divide through by a number that's not 0 because we said these x and x naught are different, I get some number here. Are we happy with this line? I can do this. I can find a number m that makes this true. OK. Now, what I really want to do is show that actually m matches this form. This is our goal. Yes?
It's not the form of derivative or?
It's not yet. We're going to try to show that it can be written in the form of a derivative. But I can't assume that it can be written in the form of a derivative. So this is actually exactly what I'm going to write. This is our goal. We show that m can be written in the form 1 over n plus 1 factorial times fn plus 1 of c for some value of c. Again, I can only write down the things I know to be true. What I know to be true is that I could certainly solve for a number to make this true. I don't know yet that I can write the number in this form, but this is where we're trying to get. Okay, so we're trying to find something that's true for some unknown value of c. We have other theorems that say under these conditions there exists some c between a and b such that whatever. What are some of those theorems that we know? Intermediate value theorem. What else? Mean value theorem. Yeah, mean value theorem, or Rolle's theorem is the simpler version of it. Yeah. So it's reasonable that we might try to use some of those theorems because those are existence theorems we already have. Those are things that say somewhere in the interval there lives a value c such that I can say something about the derivative of a function at that point c. Right? Not that I know exactly where it is, but something. So that's a hint that we've got theorems that are kind of sort of stating the sort of thing we want to do. So we probably want to use them. Because again, it's never fun to do everything from scratch every time over and over again. We should use what we know. I'm going to need a function to apply this to. So I'm going to try to define a function that looks sort of like this. But I'm going to keep x fixed. X is fixed. I'm not allowed to move x here. I'm going to actually vary the x naught. Okay, so we have fixed x here. So let's define a new function. I'll call capital F of t. So I'm going to make it look exactly like this thing here, exactly like my lowercase f that I'm trying to learn about, except that these x naughts are going to be replaced by t. So I could put in t equals x naught and get this exactly. I could put in t equals x and then get something else. Get kind of back to where I'm trying to examine things. So we're going to have f of t plus f prime of t times x minus t all the way down to 1 over n factorial, nth derivative of f at t, x minus t to the n. Okay, and then plus this remainder term here. So plus m times x minus t to the n plus 1. Is this continuous? Sure it is, right? Because little f is continuous, f prime is continuous. Okay, this is just a polynomial term. The nth derivative is continuous. Again, this is just a polynomial term. This is just a polynomial term. So capital F is certainly continuous. And, bonus, it's differentiable, right? I can take one more derivative of this, right? Because here I just go up to the nth derivative. We know that the n plus first derivative actually also exists. So I can certainly take derivatives of these terms. And again, I use my product rule throughout. Taking a derivative of this just means I need to be able to take derivatives of all these component terms. I can do that. So this is continuous and differentiable. Okay, or at least on the interval AB, we can specify that. And we mentioned that we'd probably try to use one of our earlier existence theorems, which our earlier existence theorems usually rely on the values at two endpoints that we've chosen, right? If we do intermediate value theorem, we need to know the value at the left and the value at the right. And we can do something in between. Same deal if we use mean value theorem, right? It says something about using the value at the left, value at the right, and then connecting those by a secant line. So we need to pick values, left and right values. So what are some reasonable values that I might like to plug into here in place of t? X naught and x, right? Those are sort of the key things. Clearly, I've used t in replacement of x naught, so I should probably put x naught back in there and see what happens. And the other key thing that we really care about is x. I don't care so much about the a and b. They're just sitting there saying my function behaves in here. I care about these two values. So let's try putting them in. If I put in capital F of x naught, what do I get? I get f of x naught plus, so this whole Taylor approximation plus m x minus x naught to the n plus 1. That looks long, but can I simplify this a little bit? Exactly, it's f of x. So I'll do this in one more step. All of this is my Taylor approximation, right? Evaluated at this point x. So this is Tn of x plus m times x minus x naught to n plus 1. And if you look at that for a moment, you should think, we've seen this before, we've written this down before. Actually, we wrote it down right over here. We said, we actually picked this number m so that that whole thing would be equal to f of x. So if I plug in x naught, I get something really simple. Okay, what happens now? Obviously, the other point we probably care about is x. So capital F at x. So here I get f of x. Go to the next term. Okay, f prime of x times x minus x. That's 0. Keep going through here. Again, I have an nth derivative at x times x minus x. That's 0. X minus x. This is 0. So this guy also simplifies to f of x. We believe this? Yes? All right, so I said we have some existence theorems. What one would you like me to use now? Rolle's theorem seems like a good choice, right? Intermediate value theorem, we're not in a good place for intermediate value theorem because there's no intermediate values between these two endpoints. Okay, mean value theorem we can use, but it's more complicated than we need. The simple case of mean value theorem here is Rolle's theorem, where these things are equal. So let's use Rolle's theorem. We've got everything we need for it. This guy's continuous, he's differentiable, he's equal at these 2 points. So that tells us there exists some c between x and x naught, such that, right, Rolle's theorem, function is equal at the 2 endpoints. It does something, it's got to come back down, or it goes down, it's got to come back up. Somewhere the derivative hits 0. So such that f prime of c is equal to 0. Okay, so let's try to figure out what that tells us. We know what capital F is. That means we should be able to take its derivative and plug in c and set it equal to 0 and see what we can learn from that. What we're hoping to learn from that is something about this number here. Okay, so let's see what f prime is. Well, what's that? I got a little f prime of t. Yeah, that's the first term. Now, next term, I'm going to have to do some product rule, right? I'm going to get 2 different terms coming out of here. So one of them is going to be f double prime, and this guy stays the same. The other one is that I'm going to keep my f prime and take the derivative of this with respect to t. That just pulls out a minus 1. So minus f prime of t. Okay, let's go a little more. So the next term that I would have had in here was, remember, 1/2 f double prime x minus t squared. I just write that there so that we can take the derivative more easily. Okay, so what am I going to have here? Again, I'm going to have something like a 1/2 f triple prime, and x minus t squared stays the same. Okay, and then I'm going to take the derivative of this quadratic term, right? So the 2 comes down, and we bring out a minus 1 because it's an x minus t in there. So we're going to get minus f double prime of t x minus t. And we can keep going. There's more terms. Then when we start to get to the end here, again, we do product rule on this guy. So I'm going to get 1 over n factorial. Take a derivative of my first term. I get fn plus 1 at t times x minus t to the n. Then, again, I keep getting a sign flip because of that x minus t inside the polynomial term. And n comes down, so I get a 1 over n minus 1 factorial. This guy is going to stay the same. And I get x minus t to the n minus 1. All right, so those are all my product rule terms. Then I got one more guy. Now this is just a number, so we treat him like we would always treat a constant when we're taking derivatives. We just need the derivative of this last guy. Again, a minus 1 is going to come out. We're going to get minus m. The n plus 1 comes down, and we get x minus t to the n. Okay, it looks complicated right now. There's lots of terms, but they're terms that are showing up in a pattern, right? We've got some sort of telescoping thing happening, right? So I have here an f prime, but here the minus f prime. Here I have f double prime times x minus t, but here I have minus f double prime times x minus t. Same thing here. I have a plus this term here. I'm going to have a minus this term here. Keep going. I'm going to have a plus this term here, a minus this term here. So everything is actually going to cancel itself out except for this term here and this term here. They don't cancel each other out yet until I set this equal to 0. Okay, so this telescopes so that actually f prime of t is equal to, again, this term is left. He didn't have any n plus first guy over here to cancel with. So we have to keep him. Fn plus 1 of t, x minus t to the n. And then this guy involving m is left. All right, now where were we interested in this? We were interested in this at C. We know there exists some point C where this guy vanishes. So at this point C, f prime of C is equal to all of this, where I'm just going to put in the C, x minus c to the n minus m, n plus 1, x minus c to the n, and this is equal to 0. One way that could always happen is if x is equal to c. That would do it automatically. Do I have to worry about that? That's right, I don't have to worry about it because we used Rolle's theorem. C exists somewhere between x and x naught, not at those points, but somewhere in between. Right? Our function has come up somewhere in the interior. We knew that in the interior there was either a max or a min, or maybe both. So we know there's somewhere in between these points, but not at these points where this C occurs. So we know that C is between and not equal to x and x naught. This came out of Rolle's theorem. And that means I can divide out this x minus c to the n. So this and this I can divide all the way through. And what do I get? I get that 1 over n factorial fn plus 1 of c minus m n plus 1 is equal to 0. And if I solve for m, I know now that m is equal to, okay, the n plus 1 comes down, so I get a 1 over n plus 1 factorial fn plus 1 c. And that looks suspiciously like the goal I wrote down very close to the beginning of this proof. So if I put this all back together, so we'd written down originally that f of x is equal to Tn of x plus m x minus x naught to the n plus 1. We had no idea what m was going to look like. It could be that m involved more terms like x minus x naught. It could be that it divided them out and we got something huge. It could be that it wanted higher derivatives of f, or it could be crazy. We don't know. Now we've figured out exactly what m has to be equal to. It has to be equal to this. So this is Tn of x plus 1 over n plus 1 factorial fn plus 1 of c x minus x naught to the n plus 1. And this is exactly the thing that we wanted. So this is exactly Taylor's theorem. It's actually, if you look at it stare at it a little bit, it's like a generalization of the mean value theorem. So if we were to just go with n equals 0 in here, we'd have f of x, and the 0th Taylor order approximation is just a constant term, f of x naught. Let's say f of x minus f of x naught is equal to f prime at some point times x minus x naught. So I'll just make this note. If n equals 1, we get f of x equals f of x naught plus f prime of c x minus x naught, which is our mean value theorem. Now what we've really done here by using Rolle's theorem, right? Rolle's theorem is like a special case of a mean value theorem. We've used it to bootstrap our way up to higher derivatives. Any questions on this result? Yeah. Why could we divide out by x minus c? It was because we knew that from Rolle's theorem, right? So when we did Rolle's theorem, we said we have a function that's equal at 2 points, right? And that meant either it was constant in between, and we could put c anywhere and have the derivative anywhere, or it's not constant, and that means the function comes up and gets back down. It might come up in an oscillatory way, but somewhere in the interior there was either a maximum or a minimum, right? So this was x naught and this was x. And we knew that a point C had to show up in the interior, not equal to x, not equal to x naught, but somewhere inside. So this is what Rolle's theorem said, is that C lives in between an x and x naught, and it's not equal to the endpoint values. So that's always a good question, because it can be very easy to accidentally divide by 0 in subtle ways, and this is one way you could do that. So you should be worried about that. And it works because Rolle's theorem told us actually this point will live in the middle. Yeah?
Would that be n equals 0?
Sorry, this should be n equals 0. Thank you. So let me do an example where we actually use this. So I'll do the calculator example. Okay, so we substitute e to the 0.1 into our calculator. Our calculator, I think I assumed, has 8 digits of display, something like that. Yeah, I'm assuming we have an 8-digit display, and we'd like our calculator to return those 8 digits to us correctly, and then we don't care beyond that what it's doing. Okay, so this is an 8-digit display. What does our calculator actually do? So most likely it's doing some sort of approximation, like a Taylor approximation in the background, but it has to know how many terms to keep, right? Okay, it could go to a gazillion terms, and that might be accurate, but also we don't want to sit there waiting forever. The calculator is not processing things that quickly on us. So how many terms should it compute? So we need to figure out how many terms are needed to guarantee an error of something less than, say, 5 times 10 to the minus 9. Okay, so I want the 8th decimal place correct. So the error should live in the 9th decimal place, right, which is not going to be displayed. And it should be less than 5 because I don't want things to round up and accidentally pollute my 8th decimal place. This is a 9. Okay, so this is our function, an exponential function, f of x equals e to the x. The derivatives are easy to handle in this case. Right? It's always the case that these are the derivatives. And what should my x naught be? Well, x is 0.01. We're trying to approximate things. What should my x naught be? Probably 0, right? Because I can actually evaluate these things easily at 0. Yeah.
Is that a 5 or is that S?
This is a 5. My 5s look like s's. Apologize. So let's choose x naught equal to 0. All right, and that means all of these terms equals f, this should be an nth derivative, f nth derivative of x naught. These are all equal to 1. I can do those exactly. Right, if we're using a Taylor approximation, we're rooting ourselves around some point x naught, and it should be a point where we can easily figure out what's going on. Okay, so let's write out our Taylor approximation. So we know that f of 0.1 is exactly equal to our nth order Taylor polynomial. So 1 over k factorial times 1, right? The kth derivative at x naught, which is equal to 1. Times x minus x naught to the kth power. So that's the approximation we're going to use. Or x is 0.1, yep. Plus an error term. So our error term is going to look like 1 over n plus 1 factorial. N plus first derivative. So the n plus first derivative still looks like e to the x. Now we don't get to plug in 0 anymore. Now we have to plug in this unknown point, c. So e to the c times 0.1 minus 0 to the n plus 1. Again, c, we don't know where c is, but we know some limitations on it, right? It lives somewhere between 0 and 0.1. Okay, so this is the approximation we're going to use. This is the error term. So we need to figure out what's going on with this error term, how to control that. So the error is Rn of 0.1. And I care about its absolute value, which is 1 over n plus 1 factorial e to the c times 0.1 to the n plus 1. These all happen to be positive terms in this case. Of course, if you have a trig function, they might not all be positive terms, so you'd need the absolute values. All right, e to the c. I have no idea what c is, right? I know exponential function is increasing. So I know that this is certainly less than 1 over n plus 1 factorial e to the 0.1, because c is less than 0.1, times 0.1 to the n plus 1. Okay, I don't know what this is. I mean, this is the thing we're trying to compute, right? So it's not, it would be cheating for me to now put in a value for this. So what I'm going to do is say, I don't know what this number is. It's less than 2, right? Exponential function is like 2.7, and now we're taking a 10th root of that. Or you could say it's less than 3 if you want, right? It's definitely less than 3. All right. I don't know what e to the 0.1 is, but different marker, yeah. I don't know what e to the 0.1 is, but it's certainly less than 2, let's say. Again, if you're not confident in that, you can put in 3 or whatever. Something, just some number that you're confident in. Don't get crazy and say it 10,000 because you're going to make life harder on your calculator having to do extra terms. So here we can say for our error bound that Rn of 0.1 is less than or equal to, 2. I'm calling that my bound, over n plus 1 factorial times 0.1 to the n plus 1. Okay, the error might be a lot less than this, but it's never going to be more than this. So what I'm going to do is let's require this bound to be less than 5 times 10 to the minus 9, right? This is too hard to evaluate exactly. 1, because I don't know where c is, and 2, because even if I did know where it was, I wouldn't know how to evaluate an exponential function. This is a bound on it. This is a worst case scenario. And if I can keep this less than 5 times 10 to the minus 9, I can certainly keep this less than 5 times 10 to the minus 9. Okay, so we need to find n such that 2 over n plus 1 factorial, 0.1 to the n plus 1 is less than 5 times 10 to the minus 9. You're not going to solve this explicitly for n, right? This is too nasty to solve explicitly for n. But what you can do at this point is a little bit of trial and error. And we expect when we're using a Taylor approximation, we're not using a million terms. We're probably using a few terms. So I can plug in n equals 1, and I can compute this. And that's fair, right? Asking me to compute e to the 0.1 would not be fair. Asking me to plug in n equals 4 here would be fair, because all I need to know how to do is basically multiply and divide, right? I could estimate this. So plug in different values of n. Again, you just need to know multiplication and division for that. And we should find, with n equals 6, we get, okay, 2 over 6 plus 1 factorial, 0.1 to the 6 plus 1, should be in the neighborhood of 4 times 10 to the minus 10. And that's less than my bound, which is less than 5 times 10 to the minus 9. So we know if we put in n equals 6 into here, we're guaranteed that our error is less than 4 times 10 to the minus 10. Right? It might be a lot less, it might be a little less, but it's definitely less. It's definitely going to give us our 8 digits correct on our calculator screen. Okay? So n equals 6 guarantees us, again, we don't know the exact size of the error, but it guarantees that we will get our 8 digits correct. So this is what our calculator is going to do. The calculator is going to say, all right, e to the 0.1. That's a complicated function, but let's do this. Let's do 1 plus 0.1 plus 1/2 0.1 squared plus 1 over 3 factorial, that's 6. 0.1 cubed plus 1 over 4 factorial, 0.1 to the 4th, plus 1 over, what comes next, 120, 0.1 to the 5th, plus 1 over 720, 0.1 to the 6th. And that's a fair thing to ask our calculator to do. All I need to do is know how to multiply, divide, add, right? Those are elementary operations that we want to base everything else on, right? So that's the key. This is easy. So it's easy, addition, multiplication, and division. It's easy, and it's guaranteed to be as accurate as you need it to be. So it's easy, and we have a guaranteed error bound. Any questions on that? Right, so that's just one example of Taylor's theorem. I could write down, if I had time, I could write down many others, again, with approximating differential equations, with characterizing maximum and minima of different functions. You'd use Taylor's theorem to derive your second derivative test from calculus and find out that that works. But that's one example to get you thinking about it. And I'll leave you there for today.